Okay, so I'll start with a video.
Welcome to the Centrifugal Pump Minute. Today we're talking about vibration. My name is James Farley and I'm the Griswold Product Manager. Centrifugal pumps operate at high speeds, 1800, 3600, and sometimes higher. At these speeds, high levels of vibration can be extremely damaging to the pump. Components such as mechanical seals, bearings, and couplings are going to be the first components to fail due to vibration. These can fail gradually over time, such as long-term bearing wear, or they can fail very quickly, such as a mechanical seal face cracking. We need to make sure that we're maintaining low levels of vibration to prevent these types of failures from occurring. Now, the root cause of vibration can be a lot of mechanical issues, such as unbalance of mechanical components, such as an unbalanced impeller or shaft. It can also be due to a non-rigid foundation or base plate that the pump is attached to. Sometimes you have loose bolts on your feet or soft foot conditions that can result in vibration, along with coupling misalignment, where your shafts are not aligned between the pump and the motor. Beyond mechanical issues, vibration can be caused by hydraulic issues as well. If the pump is operating with cavitation, you can get vibration in the inlet of the pump. Or if you're running the pump way off best efficiency point, you can start getting vibration as well. Vibration can be so severe that it can be seen visually. If this is the case, you need to act upon it immediately and resolve the issue. In other cases, you need instrumentation to be able to measure the vibration levels. Instruments such as handheld vibration mics can be used, where you hold the instrument up against the pump to get a vibration reading. More advanced equipment can be used to monitor vibration, such as these sensors that are attached to the pump. This can allow us to collect data continuously about the vibration levels, and we can measure triaxial vibration as well. In a production environment, you often want a permanent solution that can continuously monitor the vibration levels of the equipment. Vibration experts and advanced PdM equipment such as Safeguard are able to analyze the vibration signatures and identify the root cause. Now let's review the impact of one of the root causes of excessive vibration, coupling misalignment. The graph you're looking at shows the vibration signature for a pump operating with proper alignment and one that is misaligned. As you can see, the misaligned pump exceeds recommended vibration limits. I hope you've learned something about vibration today. Thank you for joining us.
So you ask yourself, how do machines fail? How do we detect early warning signs of failure? What's the best way to maintain machines? How do we implement vibration monitoring diagnostics? Now, like I said at the beginning, I won't go into signal analysis, interpreting the spectrum, okay? But that video gives you an idea of what form of data that comes through, okay? So when we think about maintenance, a lot of time the interest is on labor, material, and their contracts, okay? But when you think about what are the hidden costs, you think about if there's machine failure, there's issues with fines, okay? In the case of oil and gas industry now, if there are oil spills, okay, there's the community litigation issues, there's pollutions, and beyond that is the lost production cost, So you realize there is a case, and definitely we all know there is a case for improving operation and maintenance, okay? So when we talk about how machine fail, this is the popular one everyone knows, the bat curve, okay? The bathtub curve. But from experience, you realize that the bathtub curve is not the only way that depicts how machine fail. And it's because of the bathtub curve, a lot of maintenance program has always been around preventive maintenance or periodic maintenance. Okay, that's always been the key driver in the sense that once you install a brand new machine, you install it very well, you have a long useful life and you have a wear out period. So between the useful life, you could have some planned periodic interventions. Okay, that's the case. Okay, but when we look at our evolution of how equipment fail, we realize that that's not true. You can actually install a machine and it will fail because when you installed it, there was no alignment, proper alignment. There was the machine was unbalanced. Perhaps the wrong lubricant for the environment was selected. And you realize even the process of installation, even the way the installation was carried out, okay, could actually introduce some form of damages, okay, to the components. You realize that there are different ways, okay, the machinery will fail. Now, from our understanding, okay, there are 6 ways. And I'll present to you a work, 3 different, I'll kind of say 3 different analysis from United Airlines, Bloomberg, US Navy on how equipment fail, And my key interest is in these different failure profiles, which is the best? Which is the best? Just give me a second. Which is the best? Okay. So you realize that we go to the bathtub curve, our popular way. You realize if you look at the data, 3 to 4% of machines fail this way. That means 3 to 4% of machines will benefit from preventive maintenance or periodic maintenance. Now, if we look at the data, you realize more than 80% of the way machines fail, the best way to maintain is by condition-based. Okay, so let's build on that and let's look at actually, I'll skip this bit, okay, the cost element, Now, when I talk about condition-based maintenance, now I want to put a caveat, okay? Condition-based maintenance is not the best maintenance for all approach, okay? I give you a good example, especially in systems where you have redundancies, okay? If I have a redundant machinery, okay, but i.e., if this piece of equipment fails, I have a redundant equipment that I can bring online. You realize in such situations, condition-based maintenance may not be the cheapest way to do it, okay? However, when we have critical equipment, okay, whereby single point of failure, or perhaps if there's a failure, the cost impact, environmental cost impact, the lead time to repair, okay, now it begins to make that case. Now, a lot of the reactive maintenance approach, we run the equipment and when it fails, we change it, okay? It's one approach. You realize when the failure happens, okay, the cost can be heavy. The cost can be heavy, okay? But that does not mean necessarily we don't service the equipment, okay? But that's the building on that understanding, okay? We want to reduce that cost that come unplanned, okay? And we do the period maybe after every 6 months, after every 1 year. And you see that a lot in the power generation sector, whereby after 1 year, there will be maybe Series A overhaul. After the second year, there'll be Series B and Series C, okay, where they would, okay, first year, they remove some parts, the cold components, hot components, and they basically exchange the core of the engine. Now, that's based on our understanding of the bathtub curve. With that case, we can plan in the maintenance cost, okay? But you realize that when we've not used up the life of the equipment and perhaps there's still life left, the question is that the optimum point to actually maintain? And perhaps they may be due to operating conditions, okay? If it's oil and gas, okay, if there's a change in flow conditions, it could actually increase the wear and iterations of your pump, okay, of your impeller, okay? So when I have rapid wear, what do I do? Do I just wait until after 1 year, after 6 months, after 1 year to do that? Okay. And that's where comes the condition-based maintenance. Now, a lot of operators, experience of vibration based monitoring is from the area of protection. Now, gas turbines will have the emergency shutdown system, compressors, pumps, heavy duty equipment, whereby you have different alarm limits. And the vibration system most times is from the element of protection, not necessarily from the element of detecting or monitoring fault. Okay. So the question is, with the condition-based monitoring, a lot of time the resistance to it is the initial cost of the monitoring system, okay? The initial cost that comes with perhaps training and upskilling staff, okay? That's something to consider. But then once we overcome that initial monitoring cost, what is the benefit? What is the benefit? Okay, so that brings me to what's condition monitoring. Okay, so at its heart, when we talk about condition monitoring, we're talking about how do we collect information about our assets, about our machine, that a change in that variable tells us about the operating state of that machine. Okay, and there are different techniques. Now, I know I'm talking a lot about vibration, okay, but I will tell you why vibration, okay. Now, a lot of people are introduced to oil analysis, okay, where you're basically looking at the condition of the lubricant, because for a lot of equipments, apart from the fact that the lubricant allows ease of relative motion, it's also used as coolants. Okay, the lubricant can be used as coolant, even for sealing also. Okay, so we realize that by thinking about the state of the lubricant is one way of predicting the health of machines. Okay, there's ultrasonics, there's acoustic bond, there's also performance monitoring. But why then vibration? Now, if we look at the PF curve, we call it probability of failure curve, and we think about which of these techniques gives us early warning. I want to talk about early warning. We're talking about 3 to 6 months. Okay, because a lot of times, once you detect the fault, most delay is the paperwork. Okay, you raise a purchase order, depending on the item, it may be put out for tender. Okay, they select the winning bid, and that one becomes procurement. You receive it, you plan 3 to 6 months. So a lot of times, if we have that added advantage of 3 to 6 months plus, it allows us to have a controlled shutdown. Okay. Now, if we think about the techniques that we can use to detect the state or the health of machines, you see, when we have a fault, ultrasound is there. Then we have vibration, oil analysis, infrared. Now, for rotating equipment, you realize vibration is very established. We understand the vibration signature of a machine. So with vibration, we can say, this is the nature of the fault, this is where the fault is, and this is how long we have to failure. We can be that precise. Okay. Now today I won't go into the technicalities, like I said at the beginning, signal processing and the rest. Okay. But I will just touch on that. So you see, that's the reason why I'm starting with vibration, because vibration is more like, if you think about all the techniques that are developed for monitoring the health of machine, 70% of application is vibration, 20% of application is lubricant or oil analysis. Then the remaining 10%, that's where you have the infrared, ultrasonics, and you have the other techniques in operation. Okay, so let's look at the vibration monitoring. So with vibration, what we're doing is we are monitoring the vibration signature. And when we talk about vibration signature, is three things. We are either monitoring displacement, so in terms of displacement at the bearing, between the bearing and the rotor, or we are monitoring the velocity, or we're monitoring the acceleration. Now, in terms of application, you realize the monitoring is on acceleration and displacement. Okay, so when we have mostly journal bearing, larger rotating equipment, you see most of the signature we monitor is displacement. Okay, and for most cases we monitor acceleration. Okay, so the question is, what can we do with acceleration? Let me just add this in. Okay, so in terms of vibration, acceleration, velocity, displacement, those are just what we monitor. What can we detect? We can detect unbalance. Now, there are always three forces. We call it the three siblings. Okay, we call it UML: unbalance, misalignment, looseness. Okay, those three forces are always the initial complaint. Okay, it's either the rotor is unbalanced, there's issues with misalignment. And remember, even when you install a brand new machine, you have to align. And even with use of the machine goes out of alignment. Okay, so we can detect alignment, misalignment issues. We can detect looseness is issue related to wear. Now, beyond those UML, which are the basic faults, we have faults with bearing. It could be a belt drive system. It could be gearbox faults. It could also be faults from electric motor, the electromagnetic faults. Okay, it could be broken rotor bar. It could be eccentricity. It could be a short fuse. Okay, and also issues with resonance. Okay, when we have resonance in the rotating equipment that leads to piping failure. Yeah, piping failure, because once there's resonance, there could be piping failure. So you realize in the welds joints, in the short bore connections, at the instrumented wells, especially with thermocouples, you could be having breakage. Okay, so we can actually do that. So in a nutshell, you realize that it covers vibration technology covers a variety of force. So what I do now is, instead of going in depth into details of how we do it, the signal processing interpretation, okay, what I'll do is what we Carapa Engineering offer. Okay, now a lot of you will know Emerson. Okay, as a company, we are one of Emerson's trusted partners, and in delivering our own solution, okay, is leveraged on the Emerson machinery health management offering. Okay, and you think about when you want to monitor the health of machines, it could be either handheld devices. Okay, so when a lot of people are going into vibration diagnostics, they start out with a handheld device whereby they take a route, measure the vibration, and they can interrogate the data. So that's the handheld device route. Okay, at the same time, you could actually have permanently mounted sensors on your machines. Okay, and there are ways where we could go about permanently mounting, okay, the sensors. So remember, there's a difference between the protection system, which most rotating equipment will come with, okay, and the monitoring system in terms of diagnostics. Okay, so I wouldn't go in detail into what each of them entails. Okay, I'm just thinking about the time. Okay, but I would end on this note. Okay, um, I will end on this note. Okay, now in terms of vibration, we are monitoring displacement, velocity, acceleration, most cases acceleration. And with acceleration, we can do unbalance, misalignment, looseness. We can look at gearbox faults. We can look at bearing faults. We can look at issues even in bladed assemblies like pumps, compressors, cavitations. Okay, we could also monitor issues with valves. Okay, now normally when you're entering, you're thinking about, okay, in terms of lowering the cost of entry, handheld devices, route-based system, and then you build on that, you could actually have your continuously monitoring and mounted systems. Okay, now I will stop at this point. Maybe after the symposium, I'm hoping to have any further discussions, okay, with anyone who is interested to know about the AMS system and how it can be implemented. We can help you implement the system. And I will leave it at this point. And what I will do is I will stop sharing so I can welcome my colleague.